That's why minus 12. So 4 times 6 is minus 12. So this will be 8 times 10 to the power minus 9 meter 4. So this is to help you in your unit conversion. Okay, if some of you are wondering. Okay. So from here, the next step where you make mistake, or most of the students make mistake, is now stress X is equal to mz. Now is IZZ, we are clear. Now the next part that student will make mistake, what is this Y distance? Okay, what is this Y? Where is this Y we're taking? So Y is from the neutral axis or from the centroid down this direction, right? Because your Y-axis, right? This is your Y-axis, yes or no? Right? This over here is your Y-axis. So Y is equal to a certain value across this line. Y is certain, so this is Y1, Y2, Y3, Y4, and this is your Y max, right? Because that's how you label your graph. If that's your Y-axis, you label Y1, Y2, Y3, Y4. So that is the Y distance that we are talking about. And for this case, is 20 divided by what? 2. Okay. So stress in the x direction will be equal to plus or minus. For this problem, we don't care whether tensile or compression. Both will have the same magnitude because the centroid is exactly at the center. So the answer, whether tensile or compression, the answer will be the what? The same. The magnitude, the value will be the same, but the direction just change. Okay. So mz, we'll move out z, we know is what? 60. Divide by 8 times 10 to the power minus 9. And then your y is equal to 20 times 10 to the power 3 minus 2. Okay. So this will be equal to 20 power minus 3 divided by 2 times 60 divided by 8 power minus 9. So it's equal to 75. So plus or minus 75 times 10 to the power 6 Pascal. Okay. So if we were to sketch this in terms of tensile and compression, okay, so we're going to sketch this. So this is our cross-sectional area. Okay. So I'm going to draw my axis. I'm going to draw our axis that this is your y, z, rotation about x. Okay. So we're going to sketch our stress field now. So this is our stress x. Okay. And then over here, this is our y. So remember, we call this point alpha and we call this point beta, right? That's the point we call them. We call one point alpha, and then we call the other one what? Beta. Okay. Okay. So from here, we know that alpha, right? From here, we see down here, alpha is in tensile, right? Beta is in compression. So where we have over here, on the right hand side, you'll be in tensile. On the right hand side of tensile, on the left hand side will be compression, right? So when we draw this, we know point beta will be under compression. So now we sketch here. So this is how our stress field will look like. Okay. So as I mentioned before, this center part, okay, this vertical axis represents the what? The material. So it's going to be compression, it's pushing in. And then its tension is pushing out. Okay. So over here, this is where you will label this as 70 or 75. Okay, megapascal. So this is a megapascal. And the M over here, the Y is in meter. So this is 0.01. Right. So over here will be 75 minus 75 now. And then this will be equal to minus 0.01. Okay. So this is how you sketch your profile. I'm doing this because I want you to get familiar on how to sketch your profile of your stresses. Okay. Are you clear? Any questions so far? Anyone? No? Okay. So the next thing that we're going to do now, I'm going to do exactly down here also. Okay. I'm going to divide the page into two first.
Sorry, Eugene, a question.
Yeah.
Why are we using 0.01?
Because 0.01, everything is measured from the what? From the centroid. And then over here, this is the distance from the centroid.
Okay.
Okay.
Yeah, understood. Thanks.
Okay. So the next one, right, that we're going to do now. So for part B, right? For part B now, the rotation now, okay, the applied moment, the applied moment is on the y-axis. Okay. Now the applied moment. So if we're going to draw the same view, okay, we're going to draw the same view. So this is X, this is Y, this is rotation about Z. If we're going to draw the same view, okay, as before, so this is our structure now. Right, so this is our structure, same view. Now our moment, right, our moment is going to be applied in this direction. Right, so now we have moment about Y, and moment about Y will have this rotation now. Okay, so can anyone tell me how will this structure deform? Are you going to see a banana or no? Are you going to see a curvature like this or no? Anyone? How will the structure deform? Anyone? It will, how will it look like now? No takers at all? So when it's deformed, you're deformed into the page. Okay, you're deformed into the page. So this is the deformation. Do you see the banana, or do you see the smiling face or sad face deformation? You don't see it. Means you are looking at the wrong orientation. I repeat again, means we are looking at the wrong orientation. So now if we look at the other orientation, I'm going to look at my XZ plane now. Okay, so now this is my X. Over here now is my Z, right? And then based on right hand rule, this is my rotation about my y-axis. So you all know where we are looking at now, right? So now we are looking at the top now. Okay, so for the second, so this is our eye. Okay, this is our eye. Okay, this is our eye. This is our eyelashes. So moment about Z now is rotating this way. Sorry, about Y now. So the moment arrow will point upwards now. Okay, so you don't see, if you look at this view, right, the view that we have drawn initially, you don't see the curvature at all. right? You only see the thing deform, and that's how it's used. So we are looking at the wrong direction. Okay, so now if we view it from here now, right? All right, so it's thinner. So now this is a dot, and it's going to rotate this way, right? It's going to, so the top right hand rule, right? So the thumb point towards your eye, right? So your finger grip, right hand rule. So now this is your moment about y, and your moment about y again is at 60 Newton meter. So now when you view from here, the structure will now deform this way. Right? The structure will deform this way. And as I taught you before, while looking at the moment vector, you know that this, the head of the arrow, will be under compression. The tail end of the arrow will be under what? Tensor. Okay. So I'm going to call this point J, and I'm going to call this point K. Okay. So we have our point J, our point K. So the formula that we're going to use, again, the stresses we're going to find is in what direction? X direction still. Okay. So the normal stress in the X direction will be equal to my, right, over Iyy multiplied by what? Multiplied by Z. Okay. So now we are going to look at our cross-sectional view. Oh, sorry, MYY. What am I talking about? When I write, I don't. Okay. So we're going to look at our cross-sectional view. So the cross-sectional view, still the same. I'm not going to rotate my cross-sectional view at all. Okay. So this will be my Y. This will be my Z. This will be my rotation in X. Still going to draw my axis. So now this is my what? This is my ZZ. And then we are going to look at our YY now. Right? Okay, so there's our YY. So now the thing is what? Now we are interested in finding what is our what? What is our Iyy? Okay, so if you look at Iyy formula, did not really change. So Iyy is equal to width, depth, cube divided by what? 12. Okay. So the YY axis now is in this orientation now, right? This is our YY axis, is in this orientation. So remember what I told you. Parallel to the axis is our width, right? Parallel to the YY, we are interested in YY. So it's parallel to the YY axis is the width. Perpendicular to YY axis is the what? It's the depth. Okay. So now it changes, right? Now it changes. So from here, the width. So if I'm going to put out geometry, this will be 20 millimeters. Over here, this is 12 millimeters. So now your width becomes 20 multiplied by 12 cube divided by what? 12. So this will be equal to 20 times 12 power 3 divided by 12 is equal to 2880. 2.88 times 10 to the power of 3 millimeter 4, or this is equal to 2.88 times 10 to the power minus 9 meter 4. Okay. So from here, you can directly calculate your stress in the x direction is equal to my over